Hi everyone, this is Sajjad Muslihi. In this video, I'm going to talk to you about two-phase flow simulation. And actually, we're going to do this in a quarter of 5-spot injection pattern. I've put the final output of the simulation here. And actually, this is the distribution of saturations in the reservoir. Actually, we have two fluids in the reservoir. The fluid is being injected by the injection well here, and actually it's sweeping the oil toward the production well, which is located here. We could also have a fault in our reservoir, which is shown here, but actually we can change the length of this fault or even remove it. The first thing we need to do is to set up the model. I've divided the code into multiple sections, and I will run each section for you so that you can understand what is being done in each section and by the codes I've written. All right. The first lines of the code are devoted to clearing the command window, clearing the variables in the workspace, and closing the figures in case they're open on the system. Alright, so let's get started. We're going to set up the model. Here we're going to specify the reservoir geometry. Our cell dimensions are 100 by 50 by 1. In other words, we have 100 cells in the x direction, 50 cells in the y direction, and 1 cell in the z direction. Therefore, we have actually a two-dimensional model because we only have 1 cell in the z direction. Okay, we specify the number of cells that we have in each direction. Now we're going to determine what the length of each direction is. What is the length of the model in each direction? Actually, it is 100 meters in x direction, 50 meters in the y direction, and 1 meter in the z direction. So the number of cells and the length of them are the same. All right. So of course the length, the whole length of our model in the x direction is 100 meters. So each cell in the x direction or y direction or z direction is 1 meter. And we actually determine these numbers in MRST by using the function card grid. So we want to have a Cartesian grid. The first input argument of this function is the number of cells that we have in each direction that actually have been written here. Because the lengths of my model each direction is the same as the cell dimensions, I don't need to specify the second input argument of this function, and it already knows that both of them are the same. So G is the grid data structure that we have here. So we've already constructed the reservoir geometry. So I'm going to show you what it looks like. So I use the function plot grid, and the first argument is G, the grid data structure. I want the phase color to be none. I want it to have no color, and I'm going to make the edges a little bit transparent, and it will certainly look prettier. In this line, in these lines, I've made some changes to the plot that I'm going to show to you. All right, and let me run this section of the code. What happened? Actually, nothing appeared here. Let me see. Let me see what is the problem. Actually, I don't see anything here. Plot grid is okay. Oh, yeah. Now you see the plot shown here, and this is the reservoir geometry. We have 100 cells in the x direction, 50 cells in the y direction, and only one cell in the z direction. If you want to see actually um, um, you know actually the number of cells in the z direction, I can show you the plot in the three-dimensional view. Let me run this again. It's a little bit slow. It's not shown me the structure yet, so we have to wait for it. Let me do this again. Let me clear this and run it again. Maybe it will fix the problem. Yeah. Now you see the structure. Maybe it is better to see it as a figure. Now you see that we have only one cell in the z direction. Alright, so let me clear this up. Okay, now it's time to specify the rock properties. We want our reservoir to be homogeneous and also isotropic. All of our cells have 0.25 or 25% porosity, and their permeability is equal to 100 millidarcies. In the x direction, in the y direction, and also z direction. Why? Because our reservoir is isotropic. In all directions, the permeabilities are the same. We use the function makeRock to specify these properties. G, the grid structure, first argument. Second argument is the permeability, and the third argument is the porosity. And we assign this to the variable rock. Here in this line, I have specified the length of the fault using this slider. And by changing this slider, I can change the length of the fault. And actually, this is, the length is measured in cells. So here, the length of the fault is 20 cells. I can, increase it to a higher number or to a bigger number or to a smaller number. And here I have written some codes to actually to obtain the indices of the cells that I want our fault to be on. All right, and here I have set the permeability of these cells actually to epsilon, to a very extremely small number, actually that we can consider it, like 0. All right, because it's extremely small. Now it's time to show you the grid, actually the distribution of the permeability that we have in our reservoir. So we use the function plot cell data. This is the grid data structure, permeability of the cells, and here I have made the edges of actually the cells actually transparent a little bit. And there are some codes to make some changes to the graph, or to the structure that we want to see. All right. Something that I missed to tell you is this function, which is compute geometry, and actually it obtains some additional parameters like the centroids of each cell, actually the volumes of the cells that we have, and the parameters like that. And we use these parameters like centroids later in our code. All right. Uh, so we were here, and it's time to run this section of the code. It's kind of very slow. I didn't expect it to be so slow. Let me pause the video so that actually it won't be very long. Now, hopefully, my laptop works less slowly. Uh, Here I showed you the grid that we have, and here we specify the rock properties. And now we're going to see the distribution of permeabilities in our reservoir. So let me run this section of the code. And you see the grid. As you see, all these actually cells have the same permeability, and the only cells that have different permeabilities are these cells. And actually, these are the cells that our fault is located on. And their permeabilities are extremely low, as if we're going to consider them to be equal to 0. All right. Then we compute the transmissibilities. Actually, they have transmissibilities of the model, and this is the kind of transmissibility that is used in MRST. Now it's time to determine the fluid properties. The water viscosity is considered to be 1 centipoise. Oil viscosity is 10 centipoise, and water and oil densities are considered to be equal and actually to be 100 kilograms per cubic meter. And we have also, we need to calculate relative permeabilities because we need them. All right, because when we have multiple phases, we need to calculate relative permeabilities to obtain actually to use Darcy's equation and something like that. And we have used a simplified Brooks and Corey model. or some people say the Corey model. And the Corey exponents are considered to be 2, and also we have 0 residual saturations. So the equations that we use are these equations that are very simple. Now it's time to specify, actually, give the numbers to MRST. We use the function init simple fluid, and the first key value pair is written the viscosity, mu or mu. 1 is the viscosity of the aqueous phase, and 10 is the viscosity of the oleic phase. Actually, in other words, the viscosity of water and the viscosity of oil. All right. The second key value pair is density, rho. Both of densities are equal and are 1,000 kilograms per cubic meter, and the Corey exponents are 2 for both of them, or for both phases. The injection time, the time in which we're going to inject water into our reservoir, is 10 years, and during this time we're going to inject 1 pore volume in the reservoir. So the injection time is 10 years, and the rate of injection, based on the cumulative water injection and the time of injection, is expected to be this. First, we calculate the pore volume of a reservoir. Then we will divide it, by T, which is the injection time. All right. Now it's time to actually create the well model. The control type of both of the wells are BHP, or bottom hole pressure. First, we have specified actually the injection well. We have defined the injection well, and this is actually, these are in the input arguments that we need to put in this function. I'm not going to explain it to you again, because I've already talked to you, about this function. And the second well that we have defined is actually the producer, or the production well, and here the rate of injection is written here, and the rate of production must be negative, which is written here. All right, and that's it. And because we have 2 phases, we also need to define this. The aqueous phase 1, because we're going to inject water, and the oleic phase is 1 here, the second actually number that we have here, because actually we are producing oil. All right. And here we're going to plot the wells that we have in our model. So let me run this section. Now you can also see the wells that we have in our model. Actually, let me show you it in the 3-dimensional view. Now it's better. All right. So here you clearly see our structure. The injection well is here in the first cell, and the producer that we have is in the last cell in terms of indices, in terms of the cell's indices, and our fault is here. All right, let me close this figure. Now it's time to solve the equations that we have to calculate fluxes, pressures, and saturations, and things like that. We use the function init state to tell MRST what the initial conditions are. Actually, the initial pressure of the reservoir is 100 bar, and the second argument tells us that we only have oil in our reservoir. At first point, at the beginning of injection. The number of time steps that we have is 300. The value of each time step, or time step value, is equal to this. The time of injection, which is actually 10 years, divided by TSN, which is the number of time steps that we have. Alright, I have written time equal to 0 because I'm going to show you the title of each plot using this, and you will understand what I mean by this. Here I've used a for loop to actually plot multiple contours. We have used these functions to solve our equations in CompTPFA, and also the function implicit transport. We can also use the function explicit transport, but here I've used this function. But they have the same syntaxes. Alright, so I don't think, I need to explain these to you. Here I have written some lines to show you the contour, and actually it behaves like the function mesh grid, and this is the function contour f to show you the contour of our reservoir, and yeah, that's it. I think it's time to run. I've written some functions here in order to create some changes actually for the plot that we have. Alright, so let me run the main code of, or actually the last code of the script, or the live script, and you observe the model. We're actually injecting water into the reservoir, and you see the changes of the saturations that we have, and actually this fluid, which is water, is getting closer and closer to our actually production well. And here we have the fault. As you may have already noticed, the fluid, the injecting water, doesn't pass this fault, because actually we've considered it to be a sealing fault. And you see the passage of time here, 2.40 years. It will go until 10 years. And this is the color bar, 0, because we don't have any water here, to 1, because we have here 1, because actually it's completely water, and we don't have any residual oil saturation, because actually we here specified it to be, we set it to be equal to 0. where we specify the fluid properties. Here, reservoir saturation is 0. And now when breakthrough happened, and that's it. I think this is enough. Maybe it's better to stop it and actually make it a little bit smaller. Now it works much faster. Alright, I think this is enough. I'm not going to make this video very long. And actually, I've already created a video. Actually, I will show you, the complete video of this simulation at the end of the video. Alright, thank you everybody. Thank you for your time. And hope you're having a great day. Now you can see the full video of the simulation. Breakthrough occurred, and the water, the saturation of water is being increased in these areas, and also these areas as well. All right.